morning and welcome to our new chapter, Chapter 3, Oxidation Reduction Potential. At the end of this video, you will be able to describe the construction of a galvanic cell, identify the characteristics of a galvanic cell. Please be kind to prepare your pen and a chemistry notebook in order to take notes. Today, we cannot live without a laptop, cell phone, or any electric device. All the work done by these electric devices is possible because of the flow of electrons in the batteries. The kind of chemistry happening in a battery is called electrochemistry because it involves redox reactions. The reactions where electrons are exchanged, or simply oxidation and reduction reactions you've taken in the previous lesson. So how are these redox reactions involved in batteries? How do batteries work? These questions and others will be answered here in Chapter 3. Before we start, let's recall some information. Previously, an experiment was done where a silver zinc strip was placed in blue solution of copper sulfate. After some time, the blue color of copper sulfate fades, a brown deposit is formed on the zinc strip, and the mass of this zinc strip decreased. Now, this is because the oxidizing agent Cu2+ gained electrons from the reducing agent Zn. So the electrons pass directly from the zinc strip to the Cu2+ solution. Here, the Zn and the Cu2+, both reactants, are found in the same beaker. They are in direct contact. The electrons are not circulating between different compartments. This is why this experiment will give no electric energy. In order to get electric energy, the electrons must circulate. This is done with the help of something known as the galvanic cell or Daniell cell, where electrons can circulate normally between different compartments. In this way, this galvanic cell will give us electric energy. By definition, and as its name shows, an electrochemical cell is a generator that converts chemical energy into electric energy through oxidation-reduction reactions. Now, if this is an electrochemical cell, can you list some of its materials that you're familiar with from previous years? Well, if you remembered correctly, then an electrochemical cell is built using two beakers, a salt bridge, a voltmeter, connecting wires, and two distinct metals. Let's for now call them M and M'. Now, concerning the two beakers, what do you think each beaker contains? For an electrochemical cell, each beaker will contain the metallic ion of the metal used, such that in beaker 1 you will have Mn+ solution and in beaker 2 M'(N+) solution. What do we mean by that? For example, if the first strip used is copper strip, then its corresponding ionic solution is Cu2+ solution. So for this copper strip, we will place in the beaker Cu2+ solution. And if the second strip is zinc strip, then its corresponding ionic metal is Zn2+ solution. Now, how to connect these materials all together in order to get a galvanic cell? In order to construct a galvanic cell, in the first step, pour Zn2+ solution into a beaker. And then, in this beaker, place its corresponding metal, which is the Zn strip. Then in the second beaker, pour the second metallic solution, Cu2+, contained in CuSO4 solution. Then place its corresponding metal strip, which is Cu strip. In the second step, connect the two beakers by a salt bridge. This salt bridge contains an ionic compound, for example, NaCl. If we zoomed more into the salt bridge, you will find Na+ and Cl- ions. And finally, don't forget to connect the two strips by using connecting wires and a voltmeter. As you can see here, the voltmeter will show a voltage of 1.1 volts. Looking at this galvanic cell, you will feel that it's quite easy. However, there is a lot going on. For example, what's happening in each beaker? How is the mass of each metal changing? What is the function of the salt bridge? And what is the direction of the electric current? Let's answer those questions. So what is happening in each beaker or in each half cell of this galvanic cell? Given that zinc is more reactive than Cu, then what do you think will happen? Will zinc lose or gain electrons? And thus, will it undergo oxidation or reduction half reaction? What will be the correct half equation for the zinc half cell? Take a moment and choose the correct answer according to this electrochemical classification. Well, as you can see here, zinc is a stronger reducing agent than Cu. Then zinc here will lose those electrons in order to become in its ionic form Zn2+. And thus the electrons will flow from the zinc half cell into the copper half cell. So here the correct answers will be that Zn will lose electrons and thus undergo oxidation half reaction, and this will be the correct half reaction occurring at Zn half cell. Oppositely, concerning the Cu half cell, Cu2+ will gain electrons in order to become Cu metal. And thus Cu will undergo reduction half reaction, and this will be the reaction occurring at Cu half cell. So to sum up what we've said, in the copper half cell, reduction is occurring because Cu is gaining electrons. We will add here a small term, which is cathode half cell. Cathode refers to the half cell where reduction is occurring, or where the metallic ion is becoming a metal. Cu2+ will become Cu. In the second half cell, zinc is undergoing oxidation half reaction where electrons are lost. And here, this half cell will be called anode half cell because oxidation is occurring. So that in the anode half cell, the metal will lose electrons in order to become ion. Zn will become Zn2+. The overall reaction will be Zn plus Cu2+ will give Zn2+ plus Cu. Keep in mind that Cu and Zn strips represent the electrodes, or the anode and cathode of the cell. Now we've answered the first question and explained what's happening in each beaker. Let's continue on and find out what will happen to the mass of each metal. At the anode half cell, Zn is becoming Zn2+. So Zn here is a reactant and its mass will normally decrease, as shown in the following figure where Zn is losing electrons and becoming Zn2+. The mass of Zn here at the anode is decreasing. However, at the cathode half cell, Cu2+ is becoming Cu. Cu here is a product, so its mass will normally increase. This is also shown in this figure, where Cu2+ is becoming Cu and depositing on the metallic strip. Continuing on with our next question, what is the function of the salt bridge? Remember that we said that the salt bridge contains a jellified ionic solution, either KNO3, NaCl, or NaNO3, any kind of ionic solution. So here's what the salt bridge does. If the salt bridge is normally found in the electrochemical cell, the voltage rate will be 1.1 volt. However, if this salt bridge was removed, this voltage will be 0 volt. This is because the first electrochemical cell is a closed circuit. The electric current can circulate normally. However, in the second case, the electric current is cut off in its pathway. So this circuit will be open and no electric current will be read. This is concerning the first function of the salt bridge. The salt bridge ensures a closed circuit. Now, to study the second function of the salt bridge, we will concentrate on those ionic solutions. In the anode half cell of the previous electrochemical cell, we have ZnSO4 solution, which refers to Zn2+ and SO4 2- ions that are, as you can see here, initially equal. Same goes for the cathode half cell. The concentration of the Cu2+ is equal to the concentration of SO4 2- ions. And the salt bridge normally contains Na+ and Cl- ions. So what happens is that in the anode half cell, Zn becomes Zn2+. So the concentration of the Zn2+ will increase. The amount of Zn2+ ions will be much more than the SO4 2- ions. Oppositely, in the cathode half cell, Cu2+ will become Cu, and thus Cu2+ is a reactant and it will decrease in its concentration. So those Cu2+ will no longer be found. Here, the amount of SO4 2- will be much more than that of Cu2+. So that the anode half cell will be much more positive than the cathode half cell. So what's the function of the salt bridge here? There is no balance between the anode and the cathode in the charges. How to balance them? What do you think will happen to those ions, Na+ and Cl-? Take a moment and think of the answer. In order to balance the charges of the two electrodes, Cl-, the negative ion of the salt bridge, will migrate towards the anode, and the positive ion, Na+ in this case, will migrate towards the cathode. So in short, the functions of the salt bridge will be to ensure a closed circuit and to balance the charges of the cathode and anode electrodes, in a way that the positive ions will migrate towards the cathode and the negative ions will migrate towards the anode. We still have one problem to fulfill here, the direction of the electric current. First, we will start by a term which is the cell notation or the symbolic representation of a cell. This symbolic representation is a simplified way to represent a galvanic cell, where the negative pole is the anode and the positive pole is the cathode. We start up by the reactants and products of the anode, then a salt bridge, and finally the reactants and products of the cathode. For example, in this galvanic cell, the anode represents Zn, Zn2+ couple, where Zn is the reactant and Zn2+ is the product. And in the cathode electrode, Cu2+ is the reactant, which will become Cu. Between the two electrodes, we will place the term salt bridge, represented by those two lines. And this is the simplest way to represent a galvanic cell. We first learned that electrons flow from the anode to the cathode in one direction. Well, the electric current has an opposite direction from that of electrons, which is from the positive pole to the negative pole, from the cathode to the anode. And that's simply it. In this video, you've learned that an electrochemical cell is a generator that converts chemical energy to electric energy. The cell notation or symbolic representation is a simplified way to represent a galvanic cell starting from the anode to the cathode. And between them, there's a salt bridge. The direction of electrons is from the anode to the cathode, which is opposite to that of the electric current, which is from the cathode to the anode. The salt bridge has two important functions: to ensure a closed circuit and to re-establish electron neutrality between the cathode and the anode. Cations moves towards the cathode and anions will migrate towards the anode half cell. This video is prepared and recorded by teacher Zahra Ashari and supervised by teacher Hiba Badawi. Thank you for your time.